Welcome to a mesmerizing journey through the cosmos, where we explore one of the most profound theoretical scenarios in cosmology, the Big Crunch. This visualization, set against a stunning purple-blue nebula backdrop, takes us through the dramatic end of the universe as we know it, a moment where, after billions of years of expansion, the universe begins to collapse under its own gravity. The Big Crunch is a concept rooted in the Friedmann equations, which govern the universe's evolution, balancing the forces of density, curvature, and dark energy to determine its fate. In this scenario, the universe's density, denoted as ρ, becomes so great that it overcomes the expansion driven by dark energy, represented by the cosmological constant lambda, leading to a reversal where all matter, stars, and galaxies are pulled back together. What you'll see unfold is a four-stage process: an initial collapse, where fiery particles spiral inward, a struggle against dark energy, visualized by purple flashes; the formation of a singularity, marked by intense gravitational chaos; and finally, a big bounce, where cyan particles signal a new beginning. This cyclic model, inspired by theories like loop quantum cosmology, suggests the universe might be reborn from its own collapse, an eternal dance of creation and destruction. Over the next 10 minutes, we'll delve into each stage, exploring the physics, the visuals, and the profound implications of this cosmic story, inviting you to marvel at the infinite possibilities of the universe. Initial collapse. As the universe begins its dramatic collapse, we enter the first stage, the initial collapse, where the immense force of gravity takes hold, reversing billions of years of expansion. You can see fiery particles spiraling inward, drawn toward the glowing core at the center of the scene, a visual representation of stars, galaxies, and all cosmic matter being pulled together. The red wireframe sphere surrounding the core shrinks steadily, symbolizing the increasing density of the universe as it contracts. In the Friedmann equations, which govern this process, the density term ρ scales inversely with the cube of the scale factor a. As the universe shrinks, ρ skyrockets, overpowering the expansion forces. The universe's fate hinges on its density parameter, omega. If omega exceeds 1, the universe is closed, destined to collapse, a scenario we're witnessing here. The fiery trails around the core highlight the intense energy released as matter and radiation densities surge, a chaotic dance of gravitational forces at work. This collapse isn't just a physical event, it challenges our understanding of time and space as distances between all objects diminish, compressing the vast cosmos into a smaller and smaller volume. Over these 2 minutes, as the particles continue their inward spiral, we're reminded of the relentless power of gravity, a force that shapes the universe's destiny, setting the stage for the dramatic events to come, where the cosmos will face its ultimate test. Dark energy fluctuations. Now, as the collapse intensifies, we move to the second stage, dark energy fluctuations, where the universe's fate hangs in a delicate balance. Notice the purple flashes flickering across the scene, a visual representation of dark energy, denoted by the cosmological constant lambda in the Friedmann equations, as it resists the overwhelming gravitational pull. Dark energy, which once drove the universe's accelerated expansion, now fights a losing battle against the increasing density of collapsing matter. Its equation of state, W equals pressure over density, determines its behavior. If W were less than -1, dark energy could grow infinitely, potentially leading to a big rip, where the universe would be torn apart. But here, gravity prevails as the purple pulsations fade, unable to halt the collapse. Current observations, like those from the Planck satellite, estimate dark energy at about 68% of the universe's energy density, a force that shapes its fate. Yet in this scenario, its influence wanes as the universe contracts. The flickering purple particles symbolize this cosmic tug of war, a struggle between expansion and collapse, where dark energy's constant density clashes with the surging density of matter and radiation. This stage invites us to ponder alternative fates. If dark energy were stronger, the universe might expand forever into a cold, desolate void, a big freeze. But as we watch the purple flashes diminish, we see gravity's triumph, drawing the universe closer to its next critical moment, where the forces at play will reach their peak. Singularity formation. The universe now approaches its most intense moment in the third stage, singularity formation, where all matter, light, and space-time itself are compressed into an infinitely dense point. The core glows with ferocious intensity, surrounded by fiery trails, as the red wireframe sphere vanishes, symbolizing the universe's complete collapse. In the Friedmann equations, the scale factor A approaches 0, meaning the universe's size shrinks to nothing, and the density term ρ becomes infinite, a point where classical general relativity breaks down. The camera shakes violently, reflecting the gravitational turbulence as temperatures and densities soar beyond comprehension, a moment of cosmic chaos, where the laws of physics, as we know them, cease to apply. Some theories, like string theory, suggest this singularity might be a brain collision in higher dimensions, a gateway to a new state, while others propose quantum tunneling could avoid a true collapse. The trembling visuals underscore the violence of this event, where the universe reaches a critical juncture, challenging our understanding of reality. Philosophically, this moment raises profound questions. Does time itself end here, or does it transform into something beyond our grasp? As we watch the core pulse with energy, we're reminded of the limits of classical physics and the need for quantum gravity to resolve this enigma, setting the stage for a potential rebirth where the universe might find a way to defy its own destruction. Big bounce. In the final stage, we witness a remarkable turnaround, the Big Bounce, where the universe defies its collapse and emerges anew. Cyan particles explode outward from the core, symbolizing a new Big Bang. A cyclic rebirth that suggests the cosmos is eternal. This concept, rooted in loop quantum cosmology, proposes that quantum effects prevent a true singularity, smoothing out the infinite density with a quantized space-time structure, allowing the universe to rebound. As the cyan particles spread into the void, they carry the seeds of a new universe, potentially with different physical constants, where new stars, galaxies, and even life might form. The Big Bounce challenges the idea of a definitive end, suggesting an oscillating universe, as proposed by physicists like Paul Steinhardt, where expansion and contraction repeat infinitely. Visually, the scene transforms from fiery chaos to a hopeful expansion, with the camera pulling back to reveal the birth of a new cosmos, a moment of awe and wonder. This stage invites us to reflect on the universe's resilience, a cycle where destruction gives rise to creation, an eternal dance that might continue forever. As the cyan particles fill the screen, we're left with a sense of possibility. The Big Crunch is not an end, but a beginning, a testament to the cosmos's ability to renew itself, offering a profound reminder of the infinite cycles that define the universe's story.